Hi, class. This is our third lecture in chapter 12. This is going to be on chapter sections 12.4, titled Integrated Rate Laws. And this picture is a view of the science building at Columbia. This is Sugar Pine, and this is where we would be meeting if we were meeting in person. So there you are. So let's get started. So I'm going to share my screen with this PowerPoint on integrated rate laws. Let's see if this works. All right, so hopefully you can see the PowerPoint integrated rate laws. Start the slideshow. So the objectives in this chapter are to be able to specify the reaction rates in differential and integrated forms. Those are the rate equations and knowing what information each expression contains. So that's how we're going to start. Be able to calculate half-lives and concentrations from the integrated rate expressions. And so let's get started. So we'll start with the first order reaction. So if you remember previously, let me move the pictures here, my desktop there. So previously, for a simple reaction, say A going to B, the rate is expressed as the change in the concentration of A over the change in time. And for first order, that's equal to the rate constant times the concentration of A. So this would be this is expression that we learned previously for first order rate law. If we change this into the differential form, it looks like this: minus dA over dt equals Ka. And so if we want to see how this, how a change in A is a function of time, we'd rewrite it to look something like this. So this is a differential equation showing the change in A is a function of time. And this is a differential equation that we can integrate. So let's integrate it. Oops, go back. Okay, if we change it into a form that it can be integrated, we end up with A at a specific time is equal to A naught, the initial concentration, exponent to the minus KT. So this is an exponential equation, which we'll see how we can use on the next slide. So for a first order equation, there's a linear dependence of concentration in time. If we take the natural log of both sides of this differential equation, so if you take the natural log of this equation, we end up with an equation that's a log of A at any particular time, concentration of A at any time equals a log of A initially minus KT. So this, the usual form of a linear equation, it looks like this, where we have A, concentration of A is a function of time, where the slope is the rate constant. So this is what a linear, this is how we can take this exponential equation for first order rate and change it into a linear form that we can plot. So if we have a set of points, which is concentration per time, and we take the logarithm of those points and plot that versus time, if we get a straight line, that means that the reaction that we're following is a first order reaction. So here's an example of this plot. So an example of first order reaction in A. So on the left side, we just plotted A, the concentration of A versus time. And it's not straight, it's a curved line. we take the log of A and then plot it versus time, we get a straight line. And the slope is equal to minus, or K is equal to negative minus slope. So the rate constants are always positive, but if we're looking at the rate constant from the slope of a reactant, remember reactants are always disappearing. So the line's going to have a negative slope. And so the rate constant has to be minus that negative slope to come out positive. And so we can use, if we plotted this in an Excel spreadsheet, we could, Excel tells us what the slope is of that line. It would generate the equation for the line and tell you what the slope is. So the units of K in this case is just seconds to the minus 1. So this is this should say LNA over here, not just A. It should be LNA on this axis, which has no dimension. And this is time. So when you have rise, divide rise over run, slope, you're dividing by seconds. And so the unit for slope is seconds to the minus 1. That's what we learned last time in the last unit. Okay, there's other rate laws too. So if we look at the general rate law that we learned previously in the last section, for a zero order reaction, the rate is a change in A over the change in time is equal to K, and it would be A to the 0. Well, A to the 0 is 1, so it doesn't show in the equation. So it's the change in A over the change in time equals K. For first order, as we saw just a couple slides ago, the change in A over the change in time, the rate constant times the concentration of A to the 1. And for a second order, we have the change in A over the change in time is equal to the rate constant times A squared. So that makes it a second order. So here are the three general rate laws. I went through the integration of the first order to get to the integrated rate law down here. If you want to, if you know calculus, you can go through the integration of the first order and the second order, and you'll end up with these integrated rate laws shown in the second row. So for a zero order reaction, these are the linearized forms of the integrated rate equation for zero order, first order, and second order. So these are linearized. So if you plot for a zero order, if you plot the concentration of A versus time, you'll get a straight line with a slope of minus K and an intercept of A0. We already looked at the plot of log A versus time for first order. If you plot the inverse of A, concentration of A versus time, you'll get a linear line, and that's what a second order reaction plot would look like. So let's look at these plots. Here's an example of the plots. So we have a zero order, what the plots would look like for zero order here. So just the concentration of A versus time is shown in this first graph for zero order. You can see indeed it's linear. The slope is, the rate constant is negative the slope, and you could find it directly from that graph. If you plotted the log of A versus time for zero order, well, you get a curve. If you plotted the inverse of the A concentration versus time, you'd get another curve. So the only, if you take your data, you plot it, concentration of the reactant versus time, and you get a straight line, that means you have a zero order reaction. That's how you do it in a lab. And that's what you're going to be doing in your lab. You're going to be collecting concentration measurements, concentration measurements over time, and you're going to plot those, and you'll be able to decide whether the reaction you're observing is zero order, first order, or second order. For a first order reaction, we've already seen that if you take the log of the concentration and plot that versus time, you will get a straight line. And for a second order, if you take the inverse concentration versus time, you get a straight line. That's shown over here. We move a little on the far side. So what good are these integrated rate laws for? So first of all, if you have experimental data, you can plot them and you can determine whether your reaction you're observing is, or what order that reaction is and what the rate law looks like. So zero order, first order, or second order. So this is a way to determine the rate law and the order of the rate law other than doing initial rates. Remember the last slide we learned how we could determine what the rate law is if we did a number of experiments using the initial rate method. Well, this is a second method where you just follow a reaction to its completion, and then you plot the concentration versus time, and you can determine the rate law. So you can do this with each reactant or product in the reaction, or as we saw previously, you can relate the rates of each reactant to the other reactant or to the products using the stoichiometry of the equation. So once from these plots, you can determine the K. So once you know the rate constant, then you can determine the concentration at any time. And this is really useful, especially if you're trying to make something, you know how long it's going to, if you know the rate constant, you know how long it's going to take to obtain a certain yield. So there's lots of applications for that, for knowing the rate constant. The other thing is that the half-life of the reaction is easily calculated. And the half-life really only applies to the reactants. So it has to do with the time it takes for half of the reactant to disappear. So if we're talking about the molar concentration of a reactant A, the half-life occurs when the concentration is 1/2, 0.5, the initial concentration. So if you're solving an equation for half-life, you just plug in 0.5 A0 for the A concentration at any time, and that gives you, then you calculate the time for that when that occurs, and that's the half-life. So we're going to practice that on the worksheet later. So the half-life of first order reaction is a constant. And it's independent of the initial concentration. When we look at the equation for the half-life, for the zero order, first order, and second order, you will see that. That'll become obvious. On the other hand, the half-life for zero and second order reaction is dependent on the initial concentration. So that's the slide. So what we're going to do, we're going to do this worksheet 4 now. I'm going to switch views. Let me see. It doesn't work, but I'm going to stop my share. And we'll go through this worksheet. We're going to do several problems that apply these different the usefulness of these integrated equations. Okay, so what you should be seeing now is worksheet 4. I'm going to make my screen really big here. I don't know if it helps you visualize it, but I think you can make it big on your end also. Stop my video here. I'm going to start moving around because I'm going to work on this worksheet. Okay, so let's look at the first, initially at the top of this worksheet. By the way, this is a very handy worksheet to keep by your side when you're doing the homework, and also when it comes to doing a test, because it has the equations, has integrated equations here that you don't have to memorize. It has the conversions to half-life. So if you plug in 0.5 A0 for AT, then we're finding T1/2. That's how we describe the time at the half-life, T subscript 1/2. And for zero order, T1/2 equals A0, the initial concentration, divided by 2K. So you can see that the half-life is going to change as we change the initial concentration. For a first order equation, if we plug in 0.5 A0 here for A, you end up with a half-life equation that says T1/2 equals the log of 2 over K. And the natural log of 2 is, I think, negative is 0.692 or something like that. So that's the half-life. So it depends only on the rate constant itself, the half-life, not the initial concentration. If you look at the half-life for a second order, the half-life is 1 over K to the A0, the initial concentration. So in the case of this, gives you some other useful information about what kind of plot gives you a linear graph for the different orders. And then in all of these, some other information. In every case, the slope is equal to the rate constant. The negative slope is equal to rate constant. So remember, the negative slope is equal to the rate constant for reactants. For products, because products are increasing, it would be a positive slope if we were determining the rate constant from a product rather than a reactant. Okay, let's go through this. For a first order reaction, what quantity, when graphed versus time, will yield a straight line? Well, we went over that. So the quantity that graphed versus time would be the natural log. Let's look at the natural log of the concentration any time. So it's ln(a) versus time. So that's the answer there. I'll let you fill that in. Does the half-life of first order reaction depend on the initial concentration? We talked about that already. If you look at the half-life equation, there's no initial concentration in it, so the answer is no. All right, so you can answer that on your own worksheet. Question 2, for a second order reaction, what quantity when graphed versus time will yield a straight line? So let's look at the second order equation. So the quantity graphed that will yield a straight line is the quantity when graphed versus time is the inverse of the concentration at time. So we can answer that. It's 1 over A at any particular time. So that's the first part, versus time. And does the half-life of the second order reaction depend on the initial concentration? The answer is yes. Let's look at page 2. So this is a different reaction. It says the small constituent, peroxyacetyl nitrate, also known as PAN, dissociates into peroxy radicals and nitrogen dioxide in a first order reaction with a half-life of 32 minutes. So let's write down a couple things here from what's given. So it said it's a first order reaction. So we know that the equation that we're going to use is log, the natural log of PAN at any time is going to equal minus KT plus log PAN, and I kind of write over at 0 time. And just to make sure, you can go back and check the original equation to see if that's right. Let's check it. Let's look at it. So it's the log of pan minus kt plus the log of pan at time 0. So that's correct. And the t1 half is equal to 32 minutes. Since we have t1 half is 32 minutes, maybe we should also have the t1 half equation. Well, let's see what the next question. What is the rate constant for the reaction? Well, the easiest way to calculate the rate constant is from the half-life. So we remember that t1 half is equal to the log of 2 over k. And check that again, make sure that's right. Looks right. So you take my calculator. Oh, and we have to change this. We want to know the rate constant. The rate constant is k. So let's rearrange our equation. When you're solving problems using integrated rate laws, there's always a little bit of algebra involved. So if we rearrange this, we have k is equal to the natural log of 2 divided by t1 half, which is 32 minutes. So the units for k are going to be minutes to the negative 1 instead of seconds to the negative 1. And I'm trying to determine the natural log of 2, and it's 0.693. So it's going to be divided by 32 minutes. And if we do that, we get a rate constant of 0.0217 minutes to the negative 1. All right, so that's our rate constant. So we can write k is equal to 0.0217 minutes to the negative 1. Okay, so that's how you would calculate a rate constant from the half-life. Second question, if the initial concentration of pan in the air sample is 5 times 10 to the 14th molecules per liter, what will be the concentration 1.5 hours later? And so we're going to use our equation, our integrated rate law equation. So the log of pan at time t is equal to minus kt. So we wrote up here, minus kt. Well, k is 0.0217 minutes to the negative 1. T, it says the time is 1.5 hours later. 1.5 hours, but our k is in minutes, so our time has to also be minutes, so we better multiply this times 60. Let me get 60, kind of a weird looking 6 there, 60 minutes per hour. All right, so hours will cancel, we'll get 60, so that's our time. And then plus the log of A0 and A0, natural log, not log, ln. I made a mistake up there. ln. You probably saw that a long time ago. So the A0 is 5 times 10 to the minus 14, so it's natural log of 5.0 times 10 to the 14, not negative 14, 14. I'll leave the units off. So when you take the logarithm of a number, the units go away. So it's the of 5 times 10 to the 14th molecules per liter. So it looks like we can solve for the natural log of pan at time 1.5 hours. So we do this, do a little calculation here. Okay, what's going on here? The calculator just stopped working. So let me try a new calculator, this one, okay. So we have negative 0.0217 times 1.5 times 60 plus the natural log of 5.0 times 10. Oops, let's see. To the 14th. And I get 31.9 for the natural log of pan t. So we're going to take the e of that, the exponent of that, to find out what pan is. So if we take e log of pan at a particular time, e to 31.9, we'll get the value of pan. Let's try the pan at t. We get 7. So you get the concentration of pan t is 7.14 times 10 to the 13th. And that would be molecules per liter of air. Okay. Now we can say, does that make sense? And it does make sense because it should be less. So it is less. So in 1.5 hours. The other way you can kind of make sense of it, in 1.5 hours is about 3 half-lives, right? So 1.5 hours, so 32 minutes is a half-life. 2 half-lives is 1 hour. 3 half-lives is 1.5 hours. So if you divided 5 times 10 to the 14th, and we divided it by 8, that would be approximately the answer. And if you take 5 times 10 to the minus 14th divided by 8, you get 6.25 times 10 to the 13th. So that's pretty close. Okay, so I think that's right. So that's how you'd figure the concentration of pan after 1.5 hours. The third question says, how long will it take for 30% of the pan to decompose? So we're going to use that same equation, the natural log of pan at time t is going to equal to negative kt plus the natural log of pan initially. So in this case, it says when 30% of the pan decomposes. So 30% of the pan decomposes. That means there's 70% left. So that means that pan T is equal to 0.7 of pan initial, pan naught. So you take the initial is 100%, you take away 30%, you get 70%. So we could use 70% also. But 70% is 7/10 of the initial value. So that's what I like to use. You could use 70 over 100. So let's rearrange this to calculate the time. So that means the natural log of pan, rearrange this equation to calculate the time, minus natural log of pan at time 0 equals time. I'm going to do a couple of steps here, algebraic steps in a row, divided by, and this will be a negative up here, k, all right? So we have the natural log of pan t, we said is 0.7 pan at time 0 minus the natural log of pan at time 0 divided by k. If we clear the parentheses, we end up with the natural log of pan by multiplied by -1. Pan 0 minus times a minus is a plus, minus the natural log of 0.7, 0.7 pan 0. Divided by k. And this, if you're subtracting logarithms, it's really like dividing by the logarithm. So this is the natural log of pan, got all these brackets, since 0 divided by 0.7. Pan 0. So let's look like that. That whole thing divided by k. Okay, so I think we've got something that we can work with. So pan 0 cancels. So we get the log of 1 over 0.7. Give this up a little bit. Log of 1 over 0.7 divided by k. And let's see what that's going to look like. 1 divided by 0.7 comes out to be 1.42. If I take the natural log of that, 0.42. That's a 0.35. 0.35 divided by K, which we said was 0.0217 per minutes, equals 16 minutes. So there may have been a way to set that equation up a little more cleanly from the beginning. I mean, maybe we could have done this right at the beginning when, or at this point we could have changed, we could have log of pan t divided by pan at time 0 right from the get-go. And, but 60 minutes seems like a reasonable answer for that. Only 30% degraded. It's you know, somewhat less than the half-life. Okay, let's look at our next and last problem in this worksheet on integrated rate equations. So problem 4, at elevated temperatures, nitrogen dioxide decomposes to nitrogen monoxide and molecular oxygen. Start by writing and balancing the equation for this reaction. So let's do that. We'll write it over the top. So we have nitrogen dioxide, NO2, is decomposing to nitrogen monoxide. These are all gases. I'm not going to put the G there, but they're all gases, and molecular oxygen. Okay, so that's a start. We have 3 oxygens on the right and only 2 on the left, so I need to put a 2 here and probably need a 2 there because now we have 2 nitrogens. So now we have 4 oxygens on the left and 4 on the right and 2 nitrogens on the left and 2 on the right. So it's balanced. The graphs have been compiled from concentration as a function of time data for this reaction at 300 degrees. So let's look at the graphs. These are like the graphs we saw before. So this is concentration versus time and it's curved. This is log concentration versus time and it's still curved. And then in the last graph, we have the inverse concentration versus time and we get a linear equation. So that means that if we're plotting inverse versus time, that means it's a second order reaction. So is this reaction 0, first or second order? So we can write in second order here. And how do you know? Because a plot of inverse concentration versus time gives a straight line. That's how we know. Okay, so write the integrated rate law. So I'm just going to look back at my original sheet, and integrated rate law looks like this. This is T, concentration of A at times T. Actually, that's not what it looks like. It's 1 over A at time T is equal to KT plus 1 over concentration at time 0, which is the initial concentration. Using the appropriate graph, estimate the value of the rate constant for this reaction. So if we did this in Excel, it'd be easy. It'd give us the slope, but let's try this. So I'm going to use this point here. So remember the slope is rise, or what do they call it? Rise divided by run. So we'll use that point and we'll use this point. And the rise is from 175, so it's 225 minus 175. 225 minus 175 divided by 200 minus 100, that's the time. So this is the delta of 1 over A divided by the delta of T to get the rise over the run. You get 200 minus 100. So we're going to get, looks like 25 and 25 is 50. 50 divided by 100 is going to equal 0.5, and the units are m. Well, is it molarity? Not sure what the unit of concentration is. We'll say it's molarity. Seconds to the minus 1. Okay, because it's a second order reaction. So the experimenter forgot to record the initial concentration. Determine this value, showing or explaining your work below. So I'm just going to use, so the initial concentration we'll get from this equation, the original equation here. So we have 1 over, let's see, I forgot to record the initial concentration. Determine this value, showing or explaining your work below. Well, I think we can get the initial concentration off the graph. So remember, the initial concentration is the intercept, okay? We'll say the initial concentration is the intercept. So if you look at the graph, the intercept's at 125. So we have 1 over A0 is equal to 125. So that means A0 is equal to 1 over 125. So A0, that will give us the initial concentration. 1 divided by 125 comes out to be 0.008. M. Okay, we're going to say the concentration is M. So what is the half-life of this particular reaction? So again, we'll look at the, since we have the initial concentration, we can determine the half-life. And the half-life is going to be, go back to our original equation, our original, the front page tells us what the formula is for the half-life. For a second order reaction, that's what it looks like. So we're going to get 1 over, we know what K is. K we said is 0.5 molars to the -1, second to the -1, times A naught, which is 0.008 molar. So this will give us our half-life, and our half-life unit will be in seconds then. So we have 1 divided by 0.5 divided by 0.008, and we get 250 seconds. Well, let's see, does that make sense? So if a half-life is 250 seconds, so we go up to 250 seconds here, we can see that the concentration is about 250. And so if you take 1 divided by 250, it comes out to 004, which is perfect. If our initial concentration is 008, at the half-life, it should be half of that. And that's what it turns out. 1 divided by 250 is it's 250 here, sorry, 250, 1 divided by 250, or at 250 seconds, the concentration, 1 over the concentration is 250, so the actual concentration is 0.004 molar. So I hope that, I didn't show all that stuff. There it is, the work down there. Sorry about that. So there's a half-life equation. There's the value for K. There's the value for A0 that we calculated up here. We solve that, we get the half-life as 250 seconds. If you go back and look at our graph, that matches what we see in our graph. So that's it for section 12.4. And this worksheet is available for you to download and work yourself also. So goodbye, and I'll post the last section for chapter 12 on Tuesday.